Today, we are exploring the urgent challenge of decarbonizing aviation and the emergence of sustainable aviation fuel, SAF, as a ready-to-use alternative, compatible with existing aircraft and infrastructure. We delve into the technologies behind SAF production, examining how different feedstocks, including carbon dioxide, are transformed into jet fuel. From current methods to cutting-edge innovations in biological, chemical, and electrical conversion, we explore the future pathways that could reshape aviation's climate impact. Aviation fuel, commonly known as jet fuel, is derived from petroleum, much like other transportation fuels. However, unlike road or rail transport, where electrification is increasingly feasible, jetliners cannot simply be plugged into the grid. The reality is that aviation remains one of the most difficult sectors to decarbonize. This challenge is particularly urgent given that aviation contributes approximately 2.5% of global emissions and consumes nearly 300 million metric tons of fuel each year. Against this backdrop, sustainable aviation fuel, SAF, has emerged over the past decade as the most promising near-term solution for reducing aviation's climate impact. SAF offers a critical advantage: it is fully compatible with existing aircraft, engines, fueling systems, and airport infrastructure, requiring no modifications to enable its use. Unlike conventional fossil-based jet fuel, SAF is produced from renewable and low-carbon feedstocks, such as waste oils, agricultural residues, and even carbon dioxide. This enables a meaningful shift toward carbon-neutral aviation. Depending on the feedstock and production pathway, SAF can deliver 80% or more net life-cycle greenhouse gas emission reductions compared to traditional jet fuel. International organizations such as the International Civil Aviation Organization and the International Air Transport Association have set aspirational goals for the widespread adoption of SAF by 2050. Complementing these global efforts, regional bodies like the European Union and the United States have introduced binding mandates and incentive frameworks to accelerate SAF deployment. The EU's RefuelEU aviation initiative requires a minimum 2% SAF blend by 2025, scaling up to 70% by 2050. In the United States, the SAF Grand Challenge aims to produce 3 billion gallons of SAF annually by 2030 and 35 billion gallons by 2050, supported by tax credits under the Inflation Reduction Act. These mandates and policy instruments are accelerating the scale-up of commercialized SAF technologies while simultaneously driving innovation across emerging production pathways. Regardless of the specific approach, all SAF technologies, both established and experimental, follow a fundamental two-step process. In the first step, renewable feedstocks are converted into intermediate products such as bio-oils or alcohols. These intermediates are then upgraded in the second step through hydroprocessing or other refining techniques to produce SAF that meets stringent aviation fuel specifications. The selection of production technology is closely tied to the nature of the feedstock, which typically falls into one of four main categories: lipid-based feedstocks, plant oils, used cooking oil, animal fats, and non-edible vegetable oils; sugar-based feedstocks, corn, wheat, bagasse, and other carbohydrate-rich biomass; lignin-rich feedstocks, crop residues, forestry waste, and other woody biomass; carbon dioxide, captured from point sources or directly from the atmosphere. Currently, only two SAF technologies have reached commercial scale. First is hydroprocessed esters and fatty acids, HEFA for short. This pathway converts plant oils, waste oils, fats, and greases into SAF via hydroprocessing. The process involves pretreatment of plant oils followed by catalytic deoxygenation and hydroisomerization to produce jet-grade hydrocarbons. Second is alcohol-to-jet or A-to-J for short. This method processes sugar-based alcohols such as bioethanol or butanol through dehydration, oligomerization, and hydrogenation to yield SAF. Typically, corn or wheat is fermented to produce ethanol, which is then upgraded to jet fuel. While both HEFA and A-to-J are technically capable of using waste-based feedstocks, such as used cooking oil or cellulosic ethanol, the commercial reality is more complex. Current HEFA production relies on food-grade oils, and A-to-J facilities use food grains like corn. Although these technologies are classified as sustainable due to their non-fossil origins, they raise serious concerns about food versus fuel trade-offs. In a world where nearly 30% of the global population faces moderate or severe food insecurity, diverting edible resources to fuel production presents a troubling paradox. To address this, emerging technologies are being developed to utilize non-food feedstocks more effectively. Two promising pathways have emerged for non-food biomass feedstock. First of these is hydroprocessed catalytic fast pyrolysis oil, or HCFPO. This method employs catalytic fast pyrolysis, a form of thermal decomposition, to convert lignin-rich biomass into bio-oils, which are then hydroprocessed into SAF. The second process is catalytic hydrothermolysis jet or CHJ. CHJ uses hydrothermal liquefaction, a thermochemical process that mimics natural crude oil formation by applying heat and pressure to biomass. The resulting bio-crude is refined into SAF through hydroprocessing. Among the most radical innovations is the use of carbon dioxide as a feedstock, captured either from industrial point sources or directly from the atmosphere. This approach not only mitigates atmospheric carbon dioxide levels but also enables a circular carbon economy, transforming waste emissions into valuable fuel. Carbon dioxide to SAF conversion is being pursued through three primary pathways. Biological. Here, microorganisms convert carbon dioxide into intermediary products such as oils or alcohols for SAF. Chemical, where advanced catalytic systems synthesize hydrocarbons directly from carbon dioxide. And electrical, where electrochemical reactors powered by renewable energy reduce carbon dioxide into intermediates that can be refined into SAF. Europe is leading in electrochemical conversion technologies, while Australia is pioneering biological innovation. One notable example is Catoj, short for carboxylic acid to jet fuel, which uses bio-waste and carbon dioxide to produce microbial carboxylic acids. These are then converted into hydrocarbons suitable for SAF, gasoline, and diesel. A key advantage of Catoj is its streamlined process, reducing the number of steps from feedstock to fuel and improving overall efficiency, which could significantly lower production costs. Although these emerging technologies are still in early stages of development, they offer promising alternatives to food-based SAF pathways. Their success will depend on continued research, supportive policy environments, and strategic investment to bring them to commercial scale.